get started. All right, welcome everybody. I'm Emad Benjamin. I'm a staff solutions architect with VMware. I've been with VMware for about 8.5 years. I've been in the industry for about 20. And in the last 15 years, I've focused on Java, both on the development side and specifically in the last 7 years, both on the development and the runtime tuning side. So in this discussion, I'll be going into how to basically deploy a JVM on a virtual infrastructure, how to tune a JVM, and talk about GC tuning. And I'll share with you along the way some 250 customer interactions I've had in the last 18 months and the various questions that come up, and some of them are really interesting. Obviously not all the questions, but I've just kind of picked the ones that I think will help you think about how you lay out your platform. Anyone was here at my session last year? Okay. All right, let's have a show of hands. How many actual Java developers in their present job function? Okay. How many DevOps or like /admin runtime tuners? Okay. Any ESX admins? Hey. All right. So I'll actually, somebody earlier asked whether this session is specific to vSphere or not. It's not. I will cover vSphere, but about 80% of the content is on the hotspot JVM, how to tune it, and what are the tuning considerations you need to think about. All right. I guess you heard about me. So we're going to go through the high-level section here very quickly, and then the main kind of section, the technical section, is here. We'll do a deep dive. The design and sizing part of the session is really the main thing. Obviously, this is kind of a watered-down version of a workshop that I run that takes about a whole day. So I will try and hit on all of the main points. There's no way we can turn a GC tuner out of you in a day, but we'll try. I assume a lot of you, so okay, let's ask this question. How many of you have done substantial amount of GC tuning? That means at least more than 3 times in a production situation. Hey, I know you. Okay, so about 20%. All right. All right, so anytime we approach a problem, I like to think about asking questions around these 4 tiers, because almost always they're missed in the discussion, and a race to assume that there's a GC problem immediately happens. It's historical, it's legacy, I don't know why, but it's there. The first thing is, if you look at a traditional middleware platform that's typically a JVM type of platform, there could be non-JVM platforms, but I won't talk about that here. You want to think about the load balancer layer. You've got the web server layer, Java application server layer, and database server. The problem could be anywhere around here. You can't just assume it's in one section. Those are the 4 technology tiers. What's complicating this is that you have to talk to different teams that may not necessarily talk to each other. And certainly in a physical deployment, we find that that's much more so, because the load balancer guys, they're networking guys. They don't even know what a Java developer looks like, really. So it kind of makes it hard to speak the same languages. And as Java DevOps guy caught in the middle, you have to kind of run around and be the glue to try and find a solution to this problem. Well, we're starting to see a change. We're starting to see operation, especially on the West Coast, we're starting to see operations hiring Java developers for the DevOps functionality, which is very encouraging. When there's a bug, you take a thread dump and then trickle down to where the error code is, and you open up a Jira and assign it to the developer, and you're a DevOps operations guy. So we're starting to see that. But what I do see that's an interesting trend is, if you virtualize basically the load balancers, I see a lot of load balancers being virtualized, web servers being virtualized, and all of these application servers. Well, when you virtualize all of those 4 tiers that I showed you, you've got one common platform, and that's essentially VMware vSphere as the runtime, as the single OS. And when you have that, those traditional silos are immediately broken down. The networking guy no longer will not speak to the database guy or the Java developer. Because there's a common runtime, the hypervisor, then they're forced to talk to each other. Obviously, I'm not going to do virtualization 101 here. Some of it is assumed. If there are certain acronyms I use that don't make sense, stop me and I'll explain, and I'll do a drill down. And by the way, how many of you are actually using, have deployed their Java environments on vSphere or on virtual infrastructure? Good, almost half. That's great. And obviously, taking that, taking the vSphere success that we had, we made a significant investment in Spring Source and the vFabric suite and building it out. Obviously, there's been plenty of vFabric sessions out there that I hope you guys attended. Just very briefly, here is the tools section. Here are all the runtime components, TC server runtime, ERS, and then here is, there was an interesting talk on EM4J. I will not dive into EM4J. This is a balloon driver. How many of you went to the EM4J talk? Okay. So it's about being able to overcommit virtual memory more than available physical memory. Obviously, Data Director product, being able to provision databases on the fly, RabbitMQ messaging, and our data products, Gemfire and SQLfire, and then vFabric APM for monitoring, and then App Director for application deployment through blueprints. Again, that's the high level, and now we'll get into the main discussion of the session. Anytime you approach, let's say I get a call from a customer, what I eventually do is go back to the design and sizing picture that I'm going to show you here. The very first thing you want to establish when you're sizing up a Java platform, whether it's on virtual or on physical, you want to know how many JVMs you're going to put on this compute resource, be it a VM or be it a physical server. And on those JVMs, you want to know the mix of the application, application workloads. Some application workloads are throughput bound, others are basically latency bound in terms of being sensitive to latency and are more response time bound. So essentially, here to give you an example, I may pick a VM that's 2 vCPU and I'll put 1 JVM on it, and then I may put 3 WAR files that represent 3 applications that I know always go together. Well, I've certified it as a building block VM. It has 1 JVM on it. It could have more JVMs. There's not a hard and fast rule. I'd like to start with a JVM to vCPU ratio of 1 to 2, and then basically certify that. By certify, I mean, well, I ran 100 concurrent sessions, for example. So I know that with this configuration, building block VM, I know I can do 100 concurrent sessions of that particular application mix. What I'll do next is, okay, so I know that's a single VM, but what about a scale-out? My SLA says that I need 300 concurrent sessions for this application. Well, then what I'll do is I'll symmetrically scale out. By symmetrically scale out, what I mean is, if this is a 2 vCPU VM, then each one of these will be a 2 vCPU VM. The reason why I do that is because I want to simplify the load balancer layer. I want to have a load balancer layer that just quite simplistically would just direct traffic based on least connection algorithm. In other words, we'll direct equal amount of traffic all the time to these VMs based on the number of active connections are established to those VMs and JVMs. Imagine if this was a 2 vCPU building block, this was 4 and this was 8. Now your load balancer algorithm has to be of a weighted type, right? So you have to send, basically 2, 4th, and 1/8 across the 3 VMs. So typically, best practice, don't bother with that. Most load balancers are capable of handling a weighted algorithm. It becomes a maintenance headache. And also what we find is that, basically this is on an ESX host. What we call an ESX host is actually a server blade, a machine. The hypervisor will sit on top of it, and you can build many VMs on top of this ESX box of this server machine. We find that you can put as many VMs as you want and overcommit to a point of about 80%, 70 to 80% core CPU utilization, meaning the actual physical CPU that are on the box are reaching about 80%, and the virtualization overhead doesn't seem to be an issue. Beyond 80%, we start to find the virtualization overhead diverge a little bit from the physical format to about 5% greater overhead. So once you do the scale out, you've certified this server box to handle 300 concurrent sessions, just as an example. Now you know a single VM takes 100, can handle 100 concurrent sessions. An ESX box can handle 300. Now you can go about and size the rest of it. Now, I'm not going to go into a great detail of troubleshooting, but in the backup slides, I've got a troubleshooting section. Obviously, if there is an issue here, you want to resolve it and then iterate over the scale out. Sometimes you'll find over here, you have to traverse and reconfigure the building block VM. For example, let's say you decided that the building block VM was a 4 vCPU construct. And you did the scale out. Everything was working fine at the middleware layer, but then the database started getting bottlenecked. Essentially, you've over-provisioned the middleware, and you have to go back and revisit and constrain this down to something that you can handle, say a 2 vCPU. But essentially, every test plan in sizing Java platforms needs to look like this. Something along those lines. Okay, so in order to further understand the sizing, let's take a look at a VM with a JVM sitting on it. Here we have a JVM process, and I'm going to call it JVM process, not heap. This is the VM right here in blue. It needs some guest OS memory, and it needs Java process memory. Now, inside the Java process, there's the heap, and it's set by -XMX. There's also initial heap. Outside of the heap, there's the Java stack, and it's governed by -XSS. It's the thread stack. So everything that you do in Java, every execution in Java, starts with a stack. And we'll get into more stack tuning a little bit later. But essentially, a stack is outside of the heap, is native memory, and sometimes we call it off the heap. So it's important to know about that. Outside of the heap, you've got permgen area, where essentially class level information is kept there. And then this area that doesn't get talked about much, the other mem section. And inside this other mem section, you've got internal JIT information, so the compiler itself, its own internal information is kept. Socket communication, so one for send and one for receive, is kept in there. And a few other things. For example, direct buffers are kept in there. So you'll find some products that use direct buffers will actually have a large space in here. I'll show you a sizing example and some guidance on how to size that. But essentially, you've got the concept of direct memory and non-direct memory. So what do I mean by that? The direct memory comes straight from the operating system. The virtual address space memory is virtualized by the guest operating system. Question? Was that a question? Okay. And the reason, I'll show you in a second why I'll make this distinction, is because a lot of the discussions are all about this, and this gets missed. So essentially what we got, if you want to size a VM and a JVM, it's VM memory is made of guest OS memory and the JVM process memory, which is JVM memory. JVM memory is made up of the max heap, the perm size, the number of concurrent threads times -XSS, plus other mem. not paying attention to the number of concurrent threads during sizing. Imagine if you had 1,000 concurrent threads, that's problematic. And a lot of the tuning I get engaged with customers is involved around not knowing about the effects of this. So let's take a look at an example here. So we have minus XMX at about 4 gig, an initial heap equal to that. Then we'll choose a Java stack of about 256K. Now, this is JVM and OS dependent. On Linux and plus hotspot, it's 256K as a default. On Windows plus hotspot can be up to 1 meg. And here I'm modeling 100 concurrent threads. I'm choosing a perm-gen area of about 256 meg. And other mem section in this case is about 3 to 5% of this number. So it turns out that a 4 gig heap is about 4.5 gig or 4.6 gig of actual memory that's needed for the Java process. And then for the guest OS, we need another half a gig. And then it turns out that a total VM memory, or if this was a machine, of 5 gig is needed. Now, in virtualization, there's a little technique to say set reservation, which means give me actual physical memory. So the VM won't start up unless it grabs a hold of actual physical memory. But what I do see out in the field is most Java developers know about this. You know, they say we need 4 gig, we've tested out this application, we'll turn to the ESX admin or the DevOps guys and say, we've got a 4 gig heap, and DevOps guy will say, okay, so let me size a VM that's 4.5 gig because you got 4 gig heap and half a gig for the OS. For a little while it's running okay and there's a traffic burst and all of a sudden the math doesn't make sense because this section got missed. This half a gig got missed from the conversation. It was outside the heap, but still of significance. Now, when does it become significant? Well, if you've got 100 concurrent threads, it might be fine, you get under the radar. But what if you got a burst of 1,000 concurrent sessions, 1,000 concurrent threads? All of a sudden, this is much larger. In fact, I find further to that conversation between the Java developer and the DevOps guy is that they get into a traffic burst situation and there's a lot of thread stacks being allocated. DevOps guy races over to the Java developer, turns around and says, we'll just increase the heap. By doing that, what you're doing is you're squeezing out how much memory is available off the heap and worsening the situation. You should either reduce the heap or increase the amount of available memory in order to facilitate those 1,000 concurrent sessions. Go ahead, question? By default, how much memory does it take? 256K. Off the heap memory. So when we use the word memory, I want to make sure that's outside of the heap. Another question.
Is the stack overflow related to this Java stack getting used up?
Yeah, so the question is stack overflow related to minus XSS getting used up? That's absolutely right. So let's say I've got some framework that does a lot of reflection and there's a deep stack that overflows. You'll see stack overflow in the log files. The default is 256K. That really means either there's bad recursive code that you need to fix or you need to increase the stack size. And we'll find with like in-memory databases, like workloads that are memory bound, we find a huge amount of benefit of increasing the stack size. And I'll get into that a little bit later.
One more question was about the other mem part. Is there a -X option to
No. No, there's not. It's a fudge factor. Yeah. Yeah.
So the memory per thread, is it only connection threads or is it threads that you have in concurrent any of the thread pools?
So these are, so I think you're kind of mixing application server concepts. These are Java threads. So if there's an application server that maps those to something else, that's what they are. So these are actually Java threads. So, you know, most application servers will adhere to a thread pool. Let's say you allocate a thread pool. Each thread is a Java thread when it executes. Yeah.
I have a question. If you profile a Java application in one operating system, will it necessarily, under similarly load conditions, if those load conditions repeat in, let's say, another operating system, another environment, will the memory, I guess, configuration requirements stay the same?
Oh, it's an interesting question. Let me repeat the question to the audience. The question is, if I've sized a Java application and a JVM environment for one particular OS, let's say Linux, and then I move that Java application, say Windows, right? Will the memory size and the requirements stay the same? There's a complicated answer. I think the answer is yes, but there is variance because of the type representation may not be consistent. Does the JVM change? If the JVM version doesn't change, then pretty much you're okay. But if the JVM version changes, there will be differences. Are the differences significant? Probably not. That's why actually when you do migrations, it's always important to recompile from source. Even though you could take a Java application that can run on Linux and run it on Windows, it might be a good idea to recompile. Just old school kind of habits. Any other questions before we move on? Yeah. How do you determine the size? Through testing. It's application dependent, how many classes you got loaded. So it'll vary. Yeah, it throws an error. You see an error in the log file. Yeah. Ben, you got a question? You're just smiling? Okay. Okay, so let's take a look a little bit further inside the 4 gig heap. So now I'm inside the heap and taking a look at basically the young generation. I typically size the young generation to a maximum of about 33% of minus XMX. If I need to adjust, I will never go above 33%. I'll go reduce it, but never go above 33%. And that implies about 67% of the heap is left for all generation. So if we take a look at what happens at Eden space, objects are created in Eden inside young generation. In fact, if we take a step back before Eden space, there's the Java stack which gets created. It runs inside the cache registers of the CPU, and I'll show you a diagram a little bit later. And then eventually there's what they call a thread stack explosion. The objects will actually escape to Eden space, and they get allocated into Eden. So now they come into Eden, and after a while, objects die. The ones that live will move to the first survivor space, and the ones that live on again will move to the next survivor space. The movement of objects within the young generation is a reference change, basically, using a card table. So it's not as serious as what we call tenuership or promotion to all generation, which is a bit of a slower process. So objects will move to all generation, and then after some time they'll die. Some of them will die, some of them will live, and a slower process, a full GC will happen and take them out. Okay, so how do we know some of the questions we asked when we look at a log file? How do we know that 4 gig is right for us? How do we know it's not 2 gig? So through testing, what we want to establish is what we call the active live data that's inside the old generation. So in here, these are the numbers before a GC, and these are the numbers after a GC. And what I want to get to is this number here. And after a few times of full GC, I did the load testing and ran up at peak, steady state, and then look at full GCs. I want to see what's residual, what's left over in the old generation. And I see in this case that about a gig is always persisting. then I know that if there's an old generation space of 1 gig needed, I must assume that another 1 gig is about to arrive from young generation. And if I've got a 1 gig of space that I need to move around in the old generation, then I must assume that I need another 1 gig of space in the old generation to be able to move things around. So I'm kind of already at about 3.x, so 3 gig. So it turns out from empirical findings, if the active data is about 1x, then the minus XMX size, the heap size, should be somewhere between 3x and 4x. In this case, I took it to the highest ceiling of 4x. So when you're load testing, it's important to keep this kind of active data in mind. And that just summarizes what I just talked about.
Are you taking into account GC algorithms here?
No, that's the traditional throughput collector. But it pretty much still holds, even if it's, later on I'll show you a combination of throughput collector with CMS. I find that it still holds pretty closely. Actually, CMS will end up using a little bit more. About 20% more. And then I showed you like a 4 gig example. So a 4 gig JVM, 4.5 gig Java process size, and then basically total 5 gig VM. Here I'm showing you a 34 gig VM. Here we have a process, a Java process of about 32 gig, and essentially the same ratios apply up and down. So if you had larger JVMs, this is what you would do. Notice here I've used a larger stack. Okay, so we've talked about how to size a building block VM, how to scale them out, and so on. And essentially we talked about really just this box here. So if you look at a box that has about 96 gig of RAM, that's 2 socket and 8 CPUs, basically there's 8 cores on each of these sockets, the amount of memory that's available, if you're going to use virtualization, the amount of memory that's left over is about 94 gig. When you apply a 1% overhead minus 1 gig fudge factor due to VM overheads, it is variable, but 1 gig is usually more than good enough. You get about 94 gig. Now, since you've got 2 NUMA nodes, and I'm assuming these are memory-bound type of workloads, so like an in-memory database, you know, SQLfire or Gemfire, then I want to size optimally to the maximum available memory within each NUMA node. What do I mean by that? So I've got 94 gig left, divide that by 2, so I've essentially got 47 gig of high throughput memory that's available to each NUMA bank. If virtualization wasn't there, then it's basically 96 over 2. Now, I also want to pay attention when I'm sizing these systems to not vMotion heartbeat processes. Okay, so then I know that, you know, basically through a building block VM sizing and scale out sizing, how much I can put on this box. Let's just say I put on 300 concurrent sessions, but I've got about 1 terabyte of memory that I need to facilitate. Let's say I've got in the legacy system that was not sized 100 JVMs and a total RAM of 1 terabyte. Then I can say 1 terabyte divided by 96 is how many boxes I actually need in my cluster. It is really that simple. And then you get into sizing of, well, how big a JVM should be. Well, if it's going to be smaller JVMs, then I need more boxes. If I can afford larger JVMs, then you know, less ESX hosts will do the job. So what is this NUMA discussion? Why we care about NUMA so much? If you look at most x86-based hardware platforms, they are based on a NUMA architecture, meaning if you buy a server that's got 200 gigs on it, if it's 2 sockets, then the memory is split into two memory banks. Those memory banks are called NUMA banks. So the high throughput memory in this case will be 100 here and 100 there. So you want to make sure that when you're sizing these processes, they need to fit within these NUMA nodes. Now, it could be a virtual machine, or it could be a physical, like a process, a Java process that's running on a physical machine. In that case, you would have to actually pin it to the NUMA node using NUMA CTL. I have a slide on this, and we'll get into it. Oh, let me just make one point. Now, what happens if you don't actually localize your process to the NUMA node? There's a 30 to 40% degradation in memory throughput if you don't do that, because it has to go, let's say this was 100 gig, and you wanted to size a process that's about 150 gig. So there's 50 gig that needs to be fetched from the remote NUMA node. That process of fetching is going to cost you about 30 to 40% in performance degradation. It's pretty serious, especially for workloads that are memory bound, like in-memory databases. So with an ESX scheduler, what happens, we have certain NUMA optimizations. So in the old days, pre-hypervisor days, you had to use NUMA CTL to pin the process to a particular CPU and NUMA node, right? Well, ESX does that for you, essentially, as much as possible. So in this case, we've got the 47 gig that I showed you the example earlier, 94/2. I size a VM that's 47 gig. And because I've sized it like that, ESX recognizes that those VMs immediately fit nicely in a round-robin fashion onto the ESX host. That doesn't mean you just have 2 VMs, right? You could subdivide that into 4 VMs, and the sum of the 2 VMs still fits within a NUMA node, then you still NUMA local. And so on, other examples. So in this case, we do a round robin. We scheduled 4 VMs, and we got into a situation where the red pins are essentially CPU cores. They're used up. They're used up by these processes, right? These Java processes. But I've got 2 cores here that are green that are available, and 2 over here. But 2 are on one NUMA node, and the other on another NUMA node. So what happens now, in order for me to fully utilize the CPU capacity on this ESX host, I've got a 4 vCPU VM being scheduled. ESX is smart enough to actually split the execution process across the 2 NUMA nodes as much as possible, giving you local NUMA memory until it gives up and says, well, I have to interleave, I have to go back and forth. So that's another NUMA optimization that we have. And in fact, we found this out in the field, is that if you compare the NUMA optimizations that you have to do by hand on a physical system versus one that's virtualized, there's a lot more you have to do on a physical system, especially with NUMA CTL, mucking around with NUMA CTL. We also have a concept of vSocket. Basically, we can take a box that's 2-socket and make it look like 4-socket. I won't go too deeply into this. It's probably more for virtualization guys. Since we only have one ESX guy here, we'll take it offline. Let me skip over that. Now, there are some times where we get into situations like a bake-off situation where it says, hey, the physical is actually performing better than the virtual, but in actual fact, it's never an apples-to-apples comparison because the full CPU capacity of the ESX host was not used up. And what we essentially can do is size up a single VM that is as big as the box. It's not best practice, but in a performance bake-off, we were able to do that and essentially present a VM that is as big as the physical compute resource or compute capacity. And so here's the previous example, sizing large VMs, and we've tested this quite a bit. We've tested VMs up to like 90 gig heap space and multiple of terabyte clusters. But essentially those ratios still apply. One thing to notice, Java does have use NUMA Flag. It does not work with CMS. And obviously it's available in the latest update of Java 6, but it does work with a throughput collector. Now, if you're on ESX, you don't really need this flag. If you're on physical and not using CMS, then you can turn it on. Now, any memory-bound Java workload will actually need CMS. Well, you can only get it to scale and give you the right response time by using CMS. So almost always it becomes a nuisance to use this because it's not supported. It doesn't work with CMS. So what ends up happening is you need to go into where is it? NUMA CTL somewhere here. I thought I had it there. It's right here, right here. So you'd have to go and pin that JVM process to a NUMA node. So it's NUMA node 0 and NUMA node 1. Let's say if I got 2 sockets as an optimization. Another thing to do is to disable NIC interrupts. On each NIC card, so let's say you've got a compute grid, you've got 100 gig JVM on one physical box and another 100 gig JVM on another physical box, and they need to communicate over a network. It's very important to disable the interrupt coalescing. Interrupt coalescing is basically a buffering mechanism of interrupts between 2 NIC cards. Physical NIC cards communicate with each other using interrupts. But in order to reduce the amount of CPU utilized due to interrupt, they buffer, let's say, 100 interrupts at a time and send them in batches. When you do that, you increase the impact of latency, and compute grids tend to falter because they think they've come out of sync. So what you do is disable the NIC coalescing, the buffering of interrupts, and send the interrupts as they happen immediately. This increases the chatter, reduces the impact of latency, but obviously increases the CPU utilization on the physical host. This applies to physical and virtual. Now, the thing to keep in mind is that so we talked about stack tuning. On a CPU, basically you've got L1, L2, and L3. Those are cache registers. Those are registers that you do execution in before you go into NUMA. And L1 and L2 are basically per core. And L3 is shared amongst cores. On modern hardware right now, L3 can be as big as 18 meg. The L1 is like 64K, L2 maybe 128, 256K is hardware dependent. So that means I can afford to have a minus XSS that's fairly large in order to fit it into here. Now, every book that you read out there will tell you that you need to be stringent about the stack size, 256K and so on. That is true for web applications because what you're trying to do is squeeze in 1 million concurrent sessions or 10,000 concurrent sessions all within one memory space. Very small stacks, they come in and come out. But not every workload is like that. For example, compute grids, they have these fairly large fat stacks. You give them a minus XSX that's 4 meg, they'll allocate objects within that don't escape to another thread fairly quickly. Well, then why not do that? And you find the size of the L3 justifies having a larger minus XSS. In fact, a lot of the frameworks that you think give you value, they do give you value at a cost because of reflection. Reflection is deep recursion. Deep recursion means deeper stacks, more memory. So this tuning optimized, if you don't do that, what happens is you never tap into L3. You get a 256K stack, it goes into the L2 range, then it may escape to NUMA node, goes into Eden space, and so on, right? You go into memory right away. And that's not efficient. So you can execute really, really fast by having multiple stacks run inside the cache register that are on the CPU and not in memory. If you go into the BIOS, basically it's these numbers. Now, most of you would not have seen this page, so I understand, but talk to your ESX admin or hardware admin and tell them to give you these numbers. See, the level 3 cache here is 18 meg, level 2 cache is 256K, which means the minus XSS will actually fit quite nicely in the 256K per core, because we've got 8 core, But you could afford to have larger ones because you've got 18 meg there across the 8 cores. Question?
The stack size, if you use your Java application container to serve static content, like to actually stream static content like large images, which is not recommended, but if you do that, does that increase your stack size, or
does that increase your stack size? Let me think about that. So I guess it depends how you're reading the images in. I would say, you're going to spin up a thread to read the image, right? The image is, or in this case, it may not be image, it may be static content. So whatever the size of that static content is within one thread of reading, it'll try and fit into the stack. And yes, it will absolutely increase the stack size because you're loading a resource stream that's quite heavy, right? So yeah, it will increase it. Now, the good thing about that type of topology is that type of memory creation is that it's static data. It's never going to escape to another thread. We talk about the notion of object explosion. Object explosion is the concept of an object being accessed by another thread. If it is accessed by another thread, then a fatter stack is not going to help you. In your case, no one's going to access, there's no second thread accessing that data, with that static content.
so then the impact is that your thread, the amount of memory that you're allocated per thread, is just
Would need to be higher. It depends how you're ending your, like if you're reading whole, depending on what the size of the resource stream is as you read it. When you read it all in one shot, within one thread, whatever the size is, that's got to fit within.
HTTP request to a large image.
A HTTP request to a large image will not go to a JVM. Will be handled by, you're saying, well, in your case, yeah, it'll be handled by Java. A thread is spun up and a -XSS allocated. Most likely, if it's default 256K, you'll escape to Eden space on those objects. That static object will create an Eden space. Unless you're...
My XSS accordingly, have to increase it by, whatever that
Yeah.
overhead, I expect that overhead to be.
Mm-hmm. Yeah. Question? All right. So I find that some of these servers basically, by the time, the way they sell these server machines, they got a ton of memory on them, as if they're sized for like big databases. By the time you pack in the number of JVMs to fit into one box, it literally forces you to have these larger JVMs. So either you reduce the size of how much RAM you purchase on these, or you're forced to use these larger JVMs. So in this case, I have a 128 gig server, and if I assume a JVM per 2 vCPU ratio, a fairly busy JVM that's using up the CPU capacity, then in order to fully utilize all of the memory, I need a 15.84 gig heap space. 11.88 gig heap space and a Java processor of about 15.84. So keep that in mind when you're sizing as well, and we talked a little bit about it. We did a performance study here, and we found that basically this is TC server on vSphere 4.1. We found that at about 80%, as I mentioned to you earlier, that basically the overhead, okay, so let's back up a little bit. This is response time. The brown is the VM, and the blue is physical. And we compare neck and neck basically to physical at about 80% CPU utilization. Beyond that, the divergence kind of increases. So we get this question a lot from customers. I have 4 vCPUs that I want to configure VMs on. What would be the optimal configuration? In that performance study, we actually tried this out. We had a 1 VM, 4 vCPU and a 1 JVM 4 GB on it. We had 2 VMs, 2 vCPU each VM, and 2 JVMs, 2.5 gigs. So JVM 2.5 gig and a 2.5 gig. And then 4 VMs, basically 1 vCPU and 2 gig each. Okay, so let's have a vote on this. How many think the first one was the best case? How many think the second one was the best case? Right, about 10%. And what about the rest? Okay, so it's okay, so I guess you guys are right. This was the best case. And then there's ESX NUMA optimizations take a play here because these VMs are much more. There's a better opportunity for them to go to a NUMA bank that's empty. This case, I almost always do not recommend a 1 vCPU production type JVMs because if I've got a JVM that's doing a lot of work, likely that the GC cycle would take up a lot of those CPU cycles. So if the GC cycle takes a lot of CPU cycles, then what about other transactions? What about other things running on that VM? They need CPU as well, right? So I almost never recommend, unless it's development type of JVM instances that are fairly small, 512 meg and less, then maybe you could use a 1 vCPU. But almost always 2 vCPU is where I start with. Of those 250 customers that I've spoken to over the last couple of years, most common configuration I see is a VM of 2 vCPU, 1 JVM, 4 gig, and a total reservation of about 5 gig RAM. Now, what about larger JVMs? Well, I would not recommend larger JVMs on 2 vCPU. It has to be 4 vCPU plus. Reason for that is with larger JVMs, we're assuming here they're memory-bound workloads like Gem5, SQL5, type of memory grid products. You'll use a combination of CMS in the old generation and a parallel GC in the young generation. Well, you want to be able to allocate at least 2 parallel GC threads to the young generation and then leave another 2 vCPU for everything else. So imagine if it was a 2 vCPU VM and you allocated 2 threads to young generation. What about everything else? Where are they going to get CPU cycles from? So starting out with 4 vCPU for the range of about 8 to 128 gig JVM heap space is what I've noticed. Certainly when you get into 128 gig, it's likely 8 to 12 vCPU, but it is workload dependent, and you have to test for it. Another question I get from customers is, and there's a bit of a legacy here, legacy aspect of 32-bit, is that due to 32-bit 1 gig limit, a lot of companies spun up, scaled out JVMs because they needed the heap, right? So one customer had about 6,000 JVMs because they literally needed that much memory to service. And that's not the biggest, actually. I have a customer that's 10,000 JVMs. And not to mention the vendor that was telling them, they need to stay on 32-bit. It turns out that when they go to 64-bit, they can afford to consolidate a lot of their JVMs. And so what happens when you consolidate, let's say these were 1 gig, 1 gig, 1 gig, 1 gig, 2 vCPU each, let's just assume. When you consolidate, let's say you go to, say, a 2 gig JVM. When you consolidate, you just gave up the GC thread that was needed here. You don't have that anymore. You've only got 1 GC cycle here. So what you had here is 2 vCPUs and 2 vCPUs, total of 4. You're actually down to 2. Just because you vertically increase, just because you vertically double the JVM size, it doesn't mean you have to double the CPU capacity. Almost always you don't. There are corner cases, but almost always you don't. And so actually, when we're all that was said and done with that customer, their 6,000 JVMs ended up being, on 2 recommendations, a 500 JVM footprint or 1,000 JVM. So think about the administrative cost of going from 6,000 JVMs to only managing 500 JVMs. But there are times where, when we're doing the consolidation with this particular customer, there were JVMs that they claim that, hey, we can absolutely not consolidate those because there's a war file 1 and war file 2 on those JVMs, service a different line of business, and if we put them together, we can't cycle those war files and cause an impact to 2 lines of businesses as a result of 1 line of business. Well, in those cases, what we did was we consolidated the JVMs instances on a single VM so that it was a bigger VM, but at least when this peaked, it had full CPU utilization. So this was 4 vCPU. This gets the 4th vCPU. And then when this kind of was off peak, this peaked, and it had full access to the 4 vCPU. So it kind of shared the CPU usage. The other consideration is when you're sizing up large JVMs is that on day 1, you may have a 1 gig JVM that's got a web application there and a job scheduler. And all of a sudden you go to, say, 8 gig, right? And now you have to worry about your GC tuning. Well, a web application cares about response time and reduction of latency impact, while a job scheduler cares about the opposite, which is memory throughput, and it doesn't care much about latency and response time. You're compromising the amount of tuning you can do here, and what I often recommend is to separate the workload types between JVM 3 and JVM 4 and vertically scale up that way. So now we've got a JVM that only has, web services or, war files on it versus another JVM that has job scheduler on it. This is throughput tuning and this is response time tuning. So this may be a throughput GC and this may be CMS. Okay, why do we talk so much about GC? Simply because we are a Java company, but we also want to highlight that ESX doesn't really care about what GC algorithm you'll select, because Java is OS independent, and then the hypervisor makes the OS independent of the hardware. So there's 2 degrees of independence. So if there are vendors out there claiming that their JVM is only certified on their hypervisor, that doesn't make sense, right? So just thought I'd call that out. Now, doing GC tuning. So let's get into GC tuning. Well, whenever you're doing GC tuning, you're either trying to reduce latency or swapping that for increasing the amount of throughput. You're always compromising one for the sake of the other. So if I reduce the impact of latency, I'll get an improved response time, reduce latency impact, but slightly reduced memory throughput. Or I'm going to go the other way. And this may be a job scheduler. This may be a workload type that's latency, like memory bound workload. Here I've got a job scheduler. I get an improved throughput but longer response times. But it's a job scheduler. All I need to do is push a lot of data through across to the jobs, right? And there's not a user waiting to click on something and get a response, right? It's a background process. But you can never have the best of both worlds. Now I'm going to show you a CMS and a par new GC combination that gets you pretty close to this. Okay, so how do we do that? So what we're going to do is, in the young generation, we have -XMN, and it's parallel young generation using par new GC and parallel GC threads. And the old generation, we've got CMS, basically. Now, the size, remember, this is the size -XMN, this is -XMX, right? So the difference between -XMX and -XMN is the size of the old generation. Now, what we're trying to do here, basically we're trying to understand these minor GCs as they happen. Obviously they're pausing, so your application threads will be paused, but we're trying to measure the frequency of these and the duration of how long they pause for. We want to do the same thing in old generation, because our objective is to try and fit as many green threads, these are application threads, in between the GC activity. Now, in here, we're showing, basically green threads as well, but in fact, concurrent mark and sweep is mostly concurrent, meaning it does have short pauses in the mark and the remark phase, but it's mostly concurrent. So in other words, most of these can afford to have a green arrow go over the top. And this is the notion of concurrent versus parallel, right? Concurrent meaning that when GC runs, it's not pausing your application in the old generation. In the young generation, it is a throughput collector. It is parallel through multiple worker threads, kind of a consumer-producer type of design pattern. But the multiple worker threads, when they run, they will pause your application. So you get a worker thread, will pop off the queue and start collecting garbage. A green thread cannot run here, but over here it can. I probably could have done a better job on the diagram over here to show a green arrow going over the top. Next version. And then also there's survivor spaces. So survivor spaces, I usually start with survivor space ratio, a survivor ratio of about 8, which means about 10% of the size of young generation is allocated to the survivor space. For smaller JVMs, now 4 gig and less, survivor spaces at survivor ratio 8 is pretty okay, pretty good. For larger JVMs, survivor spaces can be gigs, right? And so you need to pay attention to them. And I'll show you a GC tuning recipe that drills down into that. So I've been doing GC tuning for about 15 years, and I started out, you know, it used to take 10, 12 times to get it right, QA, production, racing around, and down to, I guess these days, maybe 1 or 2 iterations. And in fact, a funny thing happened today. I have an email I was showing to a colleague of mine. I helped this company tune their GC cycle, and the customer just sent me an email, give me a graph showing that in the last 3 days there was no full GC, and he's asking me what happened to the full GCs. So we can put them back in there if you need them. But what I've learned is that there is this recipe that really holds, and that is step 8, young generation tuning. We want to measure the minor GC duration and frequency. Remember those peaks? So in other words, frequency is how often minor GC is happening, and duration is when minor GC happens, how thick is that pyramid, how long is the pause. And those are 2 numbers we're going to play around with to try and decide how many green threads or application threads we can run in between that activity. And it turns out that tuning young generation, you've only got 2 things to play around with. Minus XMN, right? Which is, by the way, absolute sizing. There are other flags which do, you know, kind of relative sizing. I don't use those. I use fixed sizing because I like to get called only once by customers, not multiple times. Or parallel GC threads. Now, when I'm tuning young generation, I focus on tuning young generation and I ignore old generation. But I take a mental note of what I actually, what changes I made in young generation. I do not tune young generation and jump to old generation, come back. I don't iterate like that. I find that that causes more headache than you know, it's less successful. So once I'm done with tuning young generation, then I'll move to old generation tuning, and I'll measure again the same thing, the duration and the frequency of major GC. And it turns out the only thing you can do in old generation is use minus XMX and adjust that, or my good friend over there, Ben Corey, built EM4J, and you could use that as an alternative to forget about a lot of this GC tuning. But anyhow, how many of you went to Ben Corey's EM4J talk? Good. So I would focus on old generation by, you know, tuning minus XMX. Now for larger JVMs, the survivor space can be multiple of gigs. So if you've got a heap space of 128 gig, you know, you could have a survivor space that's 5 gigs, right? So that's significant. You need to pay attention to that. And then so step C, we would go into a refinement of adjusting survivor ratio, starting with 8 and then adjusting it up or down. Now, what are we doing here, right? Let's take a look. What happens if I reduce minus XMN? What does that do? Well, if you reduce minus XMN, it has the impact of reducing the Eden space size And if you've got a smaller Eden space, you've got smaller memory space, now it increases the minor GC activity. But you may want to do that because sometimes the young generation is too big and the young generation pause is too high and your application is too sensitive to that amount of pause. So in order to reduce the pause, you actually would reduce minus XMN. But as you're doing that, you would increase the frequency of minor GC. As a result of adjusting minus XMN down, you've now caused the old generation to increase, right? Let's say you adjusted this by 10%, now old generation is 10% larger. Well, this causes these durations to be longer because old generation is bigger now. But it turns out it's not that bad because the gap between these two full GC activities is so large that it could be hours versus the gap here, it could be seconds, right? So one way of mitigating that is if you adjusted this by 10%, you should reduce minus XMX by 10%. So you keep things constant in old generation. What about increasing minus XMN? Well, let's say you took a look at this and you said, you know what, I could really do without that frequency of young generation. So what frequency of minor GC? And you decided to increase minus XMN by 10%. Now remember, you're reducing 10% or increasing 10%, but never increasing it beyond 33% of minus XMX. So minus XMN should never be greater than 33% of minus XMX. And the result of increasing the Eden space, effectively, since it's larger, you've actually gotten rid of one of these occurrences. And now you could fit more application threads in between. Yeah. Yeah, I just did that. You want to see it?
Yeah. Is there a way, like, why integration is always parallel? Why is it not parallel?
Good question. It's to do with the way the algorithm was written, and I think there's just so much churn inside the young generation. There's no way that they could do it concurrently. There's just not enough time to be able to do it concurrently. Time or space, I think. And yeah, so the duration increased, but you know what? I don't really care about the pause there because in between here and there, I can fit my 15 concurrent threads that I want to fit in. And then this blocks maybe 2 threads. And it ends up being a better idea. Typically, increasing my XMN up to 33% is the way to go. Decreasing it, I see less of it. On larger JVMs, I do see a practice of going down to maybe 10 or 15% minus XMN, just depending on what's happening. But not on smaller JVMs. So because we increased young generation, we caused old generation to be smaller, and as a result, there's more GC activity here. So again, to mitigate that, you want to be, if you increase this by 10%, you want to increase minus XMX by another 10% to keep things consistent. Now, what happens if I'm stuck now? I've done all of the GC tuning and I'm stuck and I still don't like this pause, right? Well, an alternative tuning is to increase the number of parallel GC threads. By increasing the number of parallel GC threads, I'm allocating more workers to do the cleaning and the pause should be smaller. Now, obviously, when you increase the parallel GC threads, you should only do it when you've got ample CPU capacity, because each thread will take up more CPU utilization. Now, what about survivor spaces? So we went step A, step B, step A, young generation tuning, step B, old generation tuning, and now survivor space tuning. I've done everything possible. I've adjusted minus XMN. I've adjusted minus XMX. Now, I've adjusted parallel GC threads, and I'm still not quite there, right? I'll take a look at survivor spaces. and then, or the animation didn't come through, we'd reduce basically survivor spaces. Now, by you reducing survivor spaces, you're causing, I don't want to say premature, but increased tenuership, meaning objects will go to the old generation a little bit faster. Now that may be okay because there's so much churn here. I'm kind of happy with the tuning that I achieved here through -XMN, parallel GC threads, and so on. I don't want to touch this anymore, but I want to negatively impact this because I can afford it. Because guess what? That customer that was saying full GC has not happened in 3 days, well, it's okay. I can afford it because on the second day I can kick off a full GC as a result of reducing survivor spaces and having better response time here. So essentially, kind of summarizing here, we're trying to, like I said, fit as many of these threads in here. So what happens is these are the configurations. We've got minor GC happening. I've got some threads, then it pauses, then some threads will run, then it pauses, then some. So, and at the same time, this is happening. So this doesn't wait for that. This is happening concurrently. Okay, so I had a listing of all of the flags that I used in here. Basically concurrent mark sweep. CMS initiating occupancy fraction of about 75%. You can have a tuning range of 51 to 75% range. That means all generation will reach 75% occupancy before there's GC activity. The customer that complained that there was no full GC activity for 3 days, he was set at 75%. I could set it at 51% and kickstart it a little bit earlier, or set it to a higher percentage and then CMS will fail into something called concurrent mode failure, which means CMS now became a throughput collector, a pausing collector, and it's forced itself into a full GC. Essentially, CMS has failed, it gave up, now it does a full GC. So we want to avoid that. So if you see concurrent mode failure in the logs, you want to avoid that by adjusting a bunch of things that we talked about, but particularly this percentage. Target survivor ratio, we talked about that. Use bias locking. So this can, if an application doesn't have high level of contention, then it can benefit from using this flag. But if it does, if there's a lot of synchronization, then it may not benefit. This biases towards the initial lock monitoring monitor owner. Max tenuring threshold, basically I limit the number of times an object is copied between survivor spaces to about 15. The default is 4, and anywhere between 4 and 15 is the sweet spot. That means it's going to get, objects are going to live in survivor spaces, copied between 4 to 15 times, depending on the number you choose, before they get tenured to old generation. In this case, parallel GC threads is set to 6, which means I have about at least 12 vCPU machine. These optimizations, by the way, compressed ops is default now, and it's only applicable to about 32 gig. Compressed ops essentially will take a workload that's inside a 64-bit JVM and treat it as if it's 32-bit by compressing the address pointer, the 64-bit address pointer, and treat it as 32-bit address pointer up to 32 gig. Beyond 32 gig, it's not in effect. And even up to 32 gig is opportunistic, meaning it depends on the type of job object. Yeah.
So which of the memory spaces does that affect?
It affects all memory spaces. By all, I mean young and old. Yeah.
The stack size?
No, not the stack size. Not the stack size. It's heap. Basically heap. These string optimizations I use these days, and I find them quite useful. you need 621 basically, but we're up to 33 now, so you should be good. Again, similar on IBM JVM, they have similar flags. Their closest to CMS and PAR new GC is this GenCon policy. Their throughput collector is this opt average pos, and their default is like a serial collector. And Ben Corey's from the J9 team can correct me if I'm wrong there. Is it? It's correct? All right, good. Thank you. And I did not pay him. Yeah, you know, there's been a lot of customers in the vSphere space. I get on a call, and I find they don't touch, and IBM doesn't tell them this. And this is true, and I'm being recorded, and that's fine. The customers will actually stay on the default, which is developer mode, a serial collector, and push out to production, and not know to switch to this or that at least. So if you have a job scheduler, you may want to adjust to this. If you have a web application or a workload that's memory bound, you want to be on GenCon. And that's an old slide. So this slide talks about a little bit about how far you can tune JVMs. I've played around with tuning 128 gig in production. I've experimented with 356 gig just as an experiment. The 356 gig was a monitoring system that was not scale out, and the vendor name shall remain anonymous. They had the whole monitoring system inside a single JVM, the 356 gig. The 128 gig was a GemFi instance in lab, and the 90 gig was GemFi instance with a customer side on a trading floor, like kind of a trading application. Well, it turns out that since Java is 64-bit, right, that means it can address 16 exabytes. But really, there's not a single OS in the world that's going to give you that kind of address space. So it turns out that, you know, 1 to 16 terabytes is the practical limit for most operating systems, and probably more like 1 or 2 for Red Hat, and probably, you know, a little bit more for SUSE, right? But there's more practical limit here that we want to talk about. I talked about NUMA, and really, it doesn't really matter what kind of memory sizes you got here. What matters is, what is the NUMA bank? So if you find you've got memory grids that need, basically they're memory bound, they're memory hungry, then you should choose servers that are 2-socket instead of 4-socket for the same amount of money, because if you've got a 100 gig server, you're going to get NUMA banks that are 50 gig each. If that same 100 gig of RAM was on a 4-socket server, then you've got 4 NUMA nodes, and they're only 25 gig each. And so your optimal range is 25 gig. You're going to have 4 JVMs, additional CPU utilization, and so on. So it's not optimal. Try and stick to the 2-socket servers for those type of applications. And that just kind of summarizes. Obviously, you know, with GC, what I've noticed is, as I mentioned earlier, enterprise web apps, less than 4 gig type of JVMs. Then you get these larger enterprise applications between 4 to 12 gig, some monitoring systems in here, and then distributed data clusters, right? Like SQLfire and GemFire type of clusters that have the need to have less JVMs, because you don't want 50 JVMs that are all talking to each other across a network, right? Maybe you want about 6 to 8, maybe 6 to 12 JVMs that are anywhere between 64 to 128 gig, or 32 to 128 gig type of JVM size, so you can manage the cluster quite feasibly, right? And when you get into this range, in fact, when you get into this range all the way to here, there's no way you're going to get the scale or the response time if you're not using CMS. And quite frankly, I think J7, G1 is not quite there yet. But it'll eventually get better.
In the earlier session that you did in the
I've not done any testing on Zing. This is Zing, the Azil Systems JVM. I don't come across it with customer. I mean, it's fairly niche type of JVM. I hardly come across it. Maybe I've come across it once in 250 customer interactions in the last 2 years. And to be honest, if you take this configuration, which I will stand by, I'm showing you 30 gig, but I've tested it 356 gig, and it scales. It actually scales up and down. Now, there is guidance. I have a SQL Fire Best Practices guide and a blog that I've written out there that talks in further detail about how to adjust these flags. What we've been able to achieve with this, we have not needed anything beyond the good old hotspot and enough computing space. So I don't, I don't see the usage for it.
So you said with this configuration you have done like 300 gigabytes.
Experimentally at 356 gig. And in a production situation, about 90 gig, and then 128 gig was a Gemfire in a lab.
Because we have 300 gigabytes in our production.
You have a 300 gigabyte single JVM?
Actually, currently we are choosing physical.
But it's a JVM, right? It's a single JVM? What type of workload is it?
I work for airlines, so we're doing kinds of pricing competitive reasons. So we get whole airlines fares, the error population.
So it's an analytics type of workload. Okay, so the way I would, so I guess your next question is how to size it for your environment. So I'm going to guess here, based on that 356 gig, and you have to adjust for each workload, right? I would obviously set this to 300 gig. Now, are you running this on Linux? Yes. By the way, the question here is that they have a JVM that's 300 gig. It's used for analytics. It's a single JVM. It's an airline industry type of workload. And so how big is this server? So
500 gigabyte memory.
okay.
Probably
48 core. Yeah, I doubt if you're going to need all of the cores.
I know that.
So basically, I would set this to 300. I would set this to start with 50 to about 100. I would NUMA CT. Okay, so if you've got 500 gig, you need to find out if it's 2-socket or 4-socket. It's 4-socket. So right there, that's not the best hardware architecture for it. Let's ignore NUMA architecture for a minute. The way you would size it is you would say 300, 100. I would size this to about 12. And that means this process is going to have potentially up to 24 CPU being utilized. You still got only about 50% of the CPU capacity left. Everything else stays the same. This would stay the same. Yeah, there's like disable explicit GC, and there's a bunch of other things that we assume customers won't do, but I didn't want to list the whole thing. But yeah, that will be your Zing replacement. So yeah.
Have you worked with any coherence customers?
Yeah, I have.
Can you speak to that?
Yeah, it's. I mean, coherence will. The funny thing is, I've only seen coherence customers only set it to about 4 gig, and I'm not sure if that's an Oracle best practice or not. But most of their JVMs are like small.
Their 18 says the biggest that they will support is 4.
18. Yeah.
The architecture team says the biggest they'll support in a production environment is 4 gigs on kernel principle.
It's which architecture team? Oracle?
Coherence.
Yeah. So that's the thing I've noticed with them, and we can talk offline. There's internal details. Obviously I want to be fair to them, but I've noticed certain things about synchronization and so on that that limit, basically the heap space. In SQLfire and GemFire, we absolutely don't have that problem. You can keep going. Whatever heap space you're comfortable with and you're willing to, test this, we can keep going. Obviously, the underlying hardware needs to be there. But that's what I've noticed. And I really don't understand how a workload is limited to a certain amount of, how can you certify a workload, based on a limit, right? It seems like a fictitious limit. Maybe it's a limit that they've tested with, but it's really dependent on the amount of RAM that's available, right? I mean, yeah, you could certify the workload, but if it's scalable, it should continue to scale. If it's not scalable and it's got a problem, then it'll fall off the cliff at 4 and 12, and I think that gives you a hint to the answer without me getting into any trouble. All right, let's move on to the next question. Yeah.
How do you determine the parallel GC threads?
Oh, so what I do, okay, so good question. I kind of forgot to mention this. In the hotspot JVM, they make this assumption that the JVM is the only thing that's going to run on physical box. So if the physical box has 8 cores or less, its parallel GC is equal to 8 cores. If it's more than 8 cores, it's equal to 5/8. Don't ask me why. It's a hotspot sun brilliance moment, right? But what I do is, again, I don't let JVM decide. I set it to 50%. So if I've got a physical box that's got 8 cores, I set 4 cores to parallel GC. And I start with that. And then if I've got plenty more CPU and I've got a GC problem, then I'll adjust it up.
What would increasing that number do?
We talked a little bit about it in one of the slides where you've got the pause in the young generation being basically too wide, right? And you've done minus XMN, survivor spaces, minus XMX, all the tuning you've already done. Increasing the parallel GC threads will minimize the pause. We'll take off a bit off the pause.
So if your ultimate goal is to put a cap on the maximum pause time, you would keep increasing that number?
You keep increasing that number. Obviously, JRocket and Azul, they try to say they have a deterministic pause, right? But I mean, essentially what you could achieve with this combination will give you that, as long as the compute resource is there. Let me see what else I wanted to cover. Yeah, and some of the best practices that we've put together here. Yeah. Now, the other problem, the question you asked about parallel GC threads, how it's determined. If hyperthreading is turned on, and you've got an 8-core physical core, and hyperthreading is turned on, that's equal to 16. So parallel GC threads would end up being set to 16. So that can't be right? It assumes nothing is actually running on that box, and it's typically vCPU allocation. We want to adjust to about 1.2 pCPU, meaning if I've got 10 physical cores with hyperthreading, I've only got really 12 or 12.5 virtual CPUs. Hyperthreading is not a doubling. We talked about this. We did a little performance study, just to quickly cover this in the last 5 minutes, and we'll open it up to more questions. And then we'll go to the book drawing. Basically, we took Spring Travel against a relational database, MySQL basically, and then a colleague of mine and I, we did basically, we wanted to simulate what a customer developer would do, download it, untuned, and test it out. So we took MySQL out, put SQLfire, did a performance test, all within a matter of days, like 1 or 2 days we were done. Both like changing the code and migrating the data, migrating the schema, and ran the test. this is what we found. We found that SQL5 stayed under 10 milliseconds, and in terms of transaction time, as number of threads were increased, but the Spring Travel with MySQL continued to track up. We also did a break test here at about 1,850 threads. MySQL version stopped responding. SQL Fire up to 3,500 threads, it was under 10 milliseconds. Then it started to look like a normal database because we wanted to keep things consistent. We overflew. We exceeded the amount of heap space that we allocated to it. So we've constrained it forcibly to make it look like MySQL. But in doing so, it continued to go up to about 7,200 threads and less than 1 second response time. So even as a disk-based database, it outperformed a traditional disk database. Then we looked at the CPU utilization at breakpoint. At 80% CPU utilization, the MySQL version was frozen. At 98% CPU utilization and 7,200 threads, SQL Fire wanted to keep going for another 2%. These were the results, and what we found is that SQL Fire scaled by about 4x and 5x to 30x improvement in response time. Okay, oops. We won't show that. Shameless plug for my book. One of you guys will be the lucky winner. That's all I had. Any questions? Anyone's got a GC problem? Go ahead.
Sorry, that parallel GC threads, is it for the young generation and old generation, or just young generation?
No, it's only for young generation. There's, yeah, go ahead.
Yeah, but then my next question, if no threads, client threads can come through, why not give it all the threads?
No, so concurrent activity, so you've got, okay, so those threads are allocated to young generation, but you've got CMS and old generation, you've got outside of the heap activity, and you've got anything else running on the OS, right? Those need CPU cycles, so you want to leave enough threads for those guys. Yeah. Okay, go ahead.
I want to ask if it's possible to have both parallel and concurrent GC for either generation?
No. So parallel, okay, so if you don't use CMS, parallel is for both young and old generation, essentially. But when you use the combination I used of CMS and old generation, CMS is only for old generation, and young generation is parallel. But it's par new GC instead of par old GC. You'll notice I used the flag called par new GC.
It's not possible to use both because I thought that
You can't, yeah, you can use CMS in young generation.
there's no concurrency.
No, someone asked the question of why not garbage collect young generation concurrently, and I want to guess here because I never worked on an internals of a JVM as a coder. Ben has, can correct me if I'm wrong there, but I think there's just too much churn inside young generation to be able to do concurrent collection, right? So there's more opportunity to move things around in old generation because there's enough spaces between pauses. But with the CMS configurations that I gave you, you should be good to go on anything from 4 to 128 and then beyond. So, any other questions?